everybody for being there and for inviting me. So of course, for the 2 days you can ask any question. There is no stupid question, especially in STEM, because if you look a little bit in the past, many microscopists didn't even know the name of STEM. They were considering it as something for, I don't know, maybe for stupid guys, or I don't know. So back maybe 15 years ago, nobody really wanted to use this for many reasons. We can discuss this later on. So my feeling, because I was more or less born with the advent of STEM, so for me it's something that I know for long, but it's not the case in the community. So if you have any question, please feel free to ask. There is absolutely no shame to have about that. Okay. So what I want to talk today, or this morning, these 2 hours, is about scanning transmission electron microscopes. And there is many things you can do with that, but coffee. And so it will be just the basic of it. And I will focus on optics, how you send electrons on your sample and what you do with it. On Ronchigrams. So Ronchigrams seems to be a very well name. It's a well name. But it's a really essential part of the STEM. So if you really want to align a STEM, it's worth knowing a little bit on Ronchigrams. And of course, I will talk about the 2 main imaging modes of the STEM: bright field and dark field. So I just give here an example. It's a true one. There is, I mean, nothing published or whatever. It's just a colleague of mine who came to me and told me, okay, you know, I'm doing some nanoplatelets of cadmium selenium. So this is the CDSE. And he told me, he was a chemist, he's a brilliant guy, and he told me, okay, it's absolutely flat, it's perfect, it's squared, and so on. So this is here a bright field image. So one way of making image with a STM, that it has been done with a corrected machine, but this is not the point here. So because it has been done with the corrected machines, you can see all black dots here are atomic columns. So it's bright field, so it's more or less like a standard CM image. So you see here a carbon foil, this background here, and you see here atoms everywhere. So this guy was kind of very happy because it was very crystalline all over the structure. And you see that there is some small change here. And you can see here as well that you see individual atoms or atomic columns. So it was very happy. So now if you look at the HADF, the dark field image, it's more or less the same. When you are a black dot, you have a white here, but it's not the only difference. The other difference is that in some parts, for example here or here, where you have a very nice image, okay, you can see dots here, you don't really see them, okay? And this gives us an information. I will come to this in a minute. And the second point is that you see that there is some part which is, the image is much brighter here, for example, than there or there and so on. And this is linked to change in the thickness. So the reason why there is change in intensity is linked to thickness. So this is not platelets, in fact. This is something else. I don't know what. It has been done 1 month ago, so I cannot tell you. But the only thing I can say is that my colleague came back to his lab crying because it was not platelets. So it's one information that he couldn't have with a regular TM for maybe 1 or 2 years. So, okay. This is just to say how powerful this can be. Okay, so the outline of my talk. So after a short introduction, I will discuss the column of the STEM. Then I will discuss about Ronchigram. The Ronchigram is just a way to make a characterization of the probe, okay, the incoming electron probe. So I have to discuss both at the same time. Then I will discuss about dark field. So HAADF means high angle annular dark field. Okay, so why is that? I will discuss a little bit during my lecture. And I will discuss bright field, which is, in fact, can be proved to be more or less exactly the same as high high resolution TM imaging. Okay. Okay, so let's begin by the beginning. So, you know, and I'm sure you had other lecture who explained that what you are doing in TM, in electron microscopy or microscopy in general, is of course image, but it does not mean that this is by anywhere an image of the reality, whatever the reality could be. It's just a result of the interaction of an electron with some materials. So everything, of course, you do in TM has to be always through in terms of a physical process that gives some change in intensity in some plane. I know it seems weird, but never forget that it's not really a reproduction of something that is really real. There is always a lot of hypotheses and assumptions. Okay, so what you do in a standard TM experiment is that you send an electron beam, which is typically 100 kilovolts. Speed is typically half the speed of light. And you send in onto a sample, and these electrons will interact with the material of interest. So there is many ways it can interact, but the first one is that it will not interact. Okay, so this is the transmitted beam. So of course, if you put some detector here, okay, and you measure the number of transmitted electrons as a function of the position of the incident electron, you will have an image, and it's a bright field image. And at the very first order, a bright field image is just an image of the presence of material or not. Okay, you have a lot of signal when there is no material, and you have no signal when there is an infinite amount of material. So at first order, it's just an image of material presence. Okay, so of course you have other kind of electrons that suffer some interaction. So this one do not interact basically, and this is all the electrons that have been elastically scattered or diffracted. Okay, and this is with this kind of signal that you can make high resolution diffraction, of course. But also if you look at very high angle, as we will see, you can make dark field image. And if you look at really high angle dark field image. Of course, this is also with this kind of electron combined with transmitted beams that you will do holography with a nice French termination. Okay, so this is almost, I think, up to this point, almost the only kind of signal you have seen in this lecture, if I'm not wrong. There is a last kind of signals that I won't, of course, discuss today, but that are more and more used in scanning transmission electron microscope. And this is signals that are used usually in scanning electron microscopes, so with no transmission. This is all the electrons that have been all the electrons like secondary electron, backscattered electron, or OG electrons. So I won't discuss this, but it's a very important class of signal. And I don't know if you got an SCM class, but if so, you have discussed this in great detail. Okay, so almost all these can be, this one are totally elastic signals. This one is, like second order signal. But all the rest of the signal will be inelastic in essence. So when you have sent this electron, it can have been diffracted, but also it can have given some energy to the medium, okay, to the sample. And so the electron will lose some energy. And if you are able to measure how many energy an electron has lost, you can make an electron energy loss spectrum or electron energy loss spectroscopy with this inelastically diffracted or scattered electrons. So this is a very important signal, and it's very important to use with an STM. It's really like twins. It's a really very good association. And with this kind of signal, you can measure like collective excitations, like plasmons, or optical signal, or individual excitation, and then you can measure, say, chemical signals. I will give some examples. So if your electron has lost some energy and gives this energy to the material, it's most likely that the material will not keep all this energy for itself. So at some time, it will do something, and what it will do, it will release this energy. So a lot of times this energy will be released in the form of phonons, so you cannot really measure them, not today, maybe in 10 years, it might be possible, but not today. So it can release energy, if you are lucky, in the form of photons, okay, light. So it can be infrared, it can be visible, and then it's coined as cathodoluminescence, and I will discuss a little bit about that during my seminar, and Louis Zagonel as well, or in the form of X-ray photons, and it's EDX, okay? And this is, well, this is a little weird, cathodoluminescence, but EDX is very, very well known, especially in conjunction with STM, for chemical analysis. So it's also like EELS, more or less. Okay, and there is a last signal, there is many other, but which is induced current, but I won't comment this. Okay, so there is a lot of information that at the end of the day may be used to make images, or maybe used to make a spectroscopy for chemical application, photonics application, or whatever. But there is one point that you don't have to forget in an STM if you really want to use it as it has to be used, is that if, like in a STEM, you have a very sharp probe, at each position of the probe, you can record many different signals in parallel, okay? When I showed you these two images have been done exactly at the same time, okay? Because the signal used to make the bright field image is different from the one used to make the HADF, and as you will see, we can make a detector arrangement that help recording both information at the same time. And it's very important because in all these points, especially when you use spectroscopy, you can make a direct link between the structure and the electronic, optical, chemical properties of your sample. It's very important, and it's not because this is atomically resolved that it's interesting. It's interesting per se. Okay. So some applications. So I show this one where it was, I think, one of the first STM image with 1 angstrom resolution, more or less. It's Batson and collaborators. So this is a gold nanoparticle here. You can see here the lattice of gold. And what you can see as well, and it's maybe more important because this kind of image could be done, say, by high resolution TM for decades. What is much more important in this is that you can track individual atoms very easily. So this is something that you don't have to forget, is that it's high angle annular dark field is especially a technique with a high sensitivity to heavy atoms. So it's very important. You can, when I say it's easy, it's really easy. If you have the good machine, having 1 atom of gold is really easy. And if you don't have if you don't have the good machine, you just have to take bigger atoms. So this is done by Crew. It's 30 years or maybe 40 now, 40 years ago. And this is the image of single atoms of uranium, so it's big atoms. But still, it's totally uncorrected machine. It's analog electronics and so on so far. But at that time, they were already, with an STM, able to detect individual atoms. So if you want to leave my lecture now, it's not a problem. You can, because the main point, when you will be on the microscope, is if you want to have a lot of sensitivity, use dark field. And then all the rest is, I mean, just blah, blah. Okay, so but please stay for my blah, blah. Another point which is very interesting with HADF or ADF is that it's essentially an uncoherent signal. So there is many ways you can explain what coherency or uncoherency is, but the point here is that you are you have a signal that do not really depend on the crystallography of your sample. So it's especially interesting to use this kind of signal when you are doing tomography, because in tomography, you are not continuously, but almost continuously tilting your sample, and it's most likely that you will have a lot of time your electron in the direction of the atomic column. You will be in zone axis, and then you will have a lot of diffraction effect in high resolution TM, which will, in a sense, kill all the important information for tomography. This is, if you do it well, not the case in HADF. So HADF is most probably the best technique for tomography. And if you want to know more about that, I'm not a good person to talk, but there will be some Spanish guy coming today, Raúl Arenal, and he knows quite well this kind of geometry. Okay. As I told you, when you are doing STM, you can use it as a microscope to measure structure, and it's especially important if you are looking at sensitivity for heavy atoms. But you can combine it with spectroscopies. So it's not the subject of my talk today, and it's a subject by itself, but I just want to show results here, where, where you have here an interface. Okay, so this is strontium titanate and barium titanate and strontium titanate, so interfaces. And if you look at this interface there, and you want to know where is the barium, where is the strontium, you can look at the HADF. You see that here the barium has a stronger signal as a strontium. We'll see why in a minute. But it may be not enough, so sometimes you want to see where the titanium is and where the barium is and where the strontium is. And this you can do with yield. So in each of these pixels, so it has been taken at the same time, a full yield spectrum has been recorded, and you can extract from this some chemical information. So here the color is coding for the kind of atoms. So of course you can do it at this scale, at the scale of single atoms, but believe me, it's not that easy. It's very nice work in the team of Janeiro Button. But this is not the point again. The point is that this is 10 years ago, more than 10 years ago. The point is that, as with HADF, you want to use an STM when you want sensitivity. So here, the sensitivity is for in yields. So of course, at the time, it was kind of state-of-the-art experiment, but it's a proof that you don't really need, in case where you don't really need spatial resolution. Here, it's gadolinium atoms within fullerenes, which are embedded in a carbon nanotube. So it's called P-pods. And the question was, can we detect these single atoms? And the answer is yes. So you have in this magenta color, coded color scale, a color code for the gadolinium atoms. In blue, you have the carbon. So that's been, this is an yield signal that has been treated in some way, analyzed in some way. And my point is that the distance between these two atoms is something like maybe 4 or 6 angstrom. I can't remember, but this is not the point. The point is that this is individual atoms. So in many applications in STM, because usually you can't have the best machine every day with the best aberration correction, so on and so forth. But at least if you have a good gun, a Schottky gun, as we will see, you really need a good gun. You will be able to make this kind of map. So you will be able to detect something like a few number of atoms, either by HADF or by chemical mapping with yield. So I could go on with many other examples. This is very recent work at the FEI company, but there is many other people doing that. This is atomic scale EDX. This is again strontium titanate. When you don't know what to study, you study strontium titanate. It works for almost all techniques as a proof of concept. But the point is that you can make chemical imaging also with EDX. And there is other things you can do. I will not comment now, but it's essentially plasmon mapping, because I will discuss this this afternoon. and luminescence mapping, okay, detecting luminescence of quantum emitters at very small scale. But my point, again, is that you have a huge sensitivity, a sensitivity that I think beat almost all other TM techniques. Okay, so this was a kind of long introduction. So now we are going into the depths of my talk. Okay. An STM, in fact, is a very, very simple machine. So I think the main reason why it has not been so developed is that you need a good electronics. So back 30 years ago, everything was analog, so it was a little bit difficult. But now that we have all this digital electronics and you have all the computer science behind, it's, I think, a little bit easier to build an STM than a TM. If you discuss with a manufacturer. Anyway, so the basic idea is that you just need an objective lens, and somewhere very far from this objective lens, you need maybe 2 detectors, simple detectors, and that's it. So of course you need a sample, because otherwise you won't do a lot, but essentially you just need an objective lens and some detector, and a sample in between. So what's the main idea? You have a gun somewhere, and you make a parallel beam that hits this objective lens. So as we will see, of course, there is more optics. That's the idea. And with this objective lens, you will form a spot on your sample. Okay. The main property of this spot, the size, the current you have in it, will be controlled essentially by an aperture that, in the STM language, we call objective aperture, but in most TM, commercial TM, are coined as condenser aperture. So you might be more, you might know much better the condenser aperture than the objective aperture in this situation. You form this probe, and you put some detector either at high angle. So this one is a high angle annular dark field detector. So annular is just because this is just a cross section, but the reality is that you have a circle, a ring, and you put some detector either at high angle. So this one is a high angle annular dark field detector. So annular is just because this is just a cross section, but the reality is that you have a circle, a ring, or you have the bright field detector, which is just along the optical axis. Okay, and that's it. So of course, if you have only that, it's a little bit boring because your probe will stay here forever. So you need some scanning coils to move the probe on the sample, and at each position of the probe, you will try to record some signal. We will see this in a minute. So that's all. It's really a simple design. In a sense, it's very robust. So this is what you buy. Okay, you buy just the TM, of course, not the operator, just the TM, like that. And it's kind of funny because if you think a little bit about that, the gun is here. You know, all of you here know that. So the gun is here. And in an STM, so the gun is here, and the condenser lens are here, and I don't know the title, so this is the corrector. So most probably the objective lens is here. I don't know. Yes, it's here. But the point is that this guy is very high and may move and whatever. So there might be a lot of mechanical fluctuation. And you may wonder why we don't want to put this part on the ground. It will make sense if you make an STM, because the most critical part is the part which is forming the probe. What happens after is totally irrelevant. Just like in a TM, the most important part is the bottom part. It's the second part of the objective lens and the projectors. What happens in the condenser is not very relevant. And in fact, okay, the first STM, dedicated STM, did have their gun on the ground. And the only manufacturer which is doing only STM, namely Nion, is also keeping this arrangement. So the gun is here, in fact, and you have the columns there. So from now on, I will use this convention to put the gun on the ground and the detector on the top. Okay, and we will see after this description that there is another meaning of doing this. Okay, so in a dedicated STM, what you will have? You will have a gun, an electron gun, of course. You will have some aperture, which are a little bit different from the one you may use in your microscope, but not so different. You will have condenser lens, like in a TM, scanning coils, an objective lens, a specimen, of course, projector lens, and a bunch of detectors. So let's look a real one. So the gun is here, as I said, condenser. So here it's an aberration correction. It's an ion machine. You have a sample stage with the objective lens here, some projectors, and some detectors, and some ears detectors. Okay. So let's do this step by step. So first of all, you have a gun here, and of course this gun is here to make to give some electrons. But one point is that what you want as a gun is a gun that has the highest brightness. So brightness, as you probably know, is a quantity which is the intensity divided by the area and divided by the solid angle. Okay. So you might ask what area, what solid angle. It does not matter. So you take a column, and a theoretical column which has absolutely no aberration. You can have any aperture you want or whatever, and this quantity is kept constant. It's conserved all through the machine. So, for example, you can define the brightness on the sample here, and it will be the intensity that hits the sample divided by the area of the probe, under the probe, and the angle of incidence. And what you want is the highest possible brightness. You don't really want a lot of current, because when you make STM, you want a very small probe. That's the most important thing. And you want to have the most current in that probe. You don't care that you have a lot of current everywhere else. That's really the brightness that is important. And this is the reason why if you try to make an STM with a Lab 6, for example, gun, or even worse with a thermal tungsten tip, you are likely to make something stupid. So nowadays, and especially in this infrastructure, you have Schottky field emission guns. So if you want to make HADF, I hope you will want to make it at the end of my talk. You have to go to this kind of gun. Otherwise, it's most likely worthless. Okay, so this is for the gun. This is really the critical part, I would say, of machine, of this kind of machine. So now the condenser lens. So here, this is a scheme with two condensers. Nowadays, most of the machines have at least 3 condensers, some mini lens and so on. And this guy here, this set of condensers define the probe size, the angle, the incidence angle, and the current. So you have 3 different variables. So that's why nowadays you have at least 3 different condensers, so that you can so that you can tune the probe size, the angle of incidence, and the current independently by a combination of the 3 different condensers. Okay. So in STM words, usually we like to say that this condenser defines the source demagnification. So it means that you have the source on your gun, which is kind of small and or too big, usually, and you want to make it smaller. So you want to demagnify it on the sample. Okay, and of course, if you want to define the current and the angle, you need an aperture somewhere. It can be before the condensers, somewhere inside the condenser or after the condensers. It will really depend on the setup you are using. but of course it's helpful to have an aperture, especially because you have a lot of aberration in a TM, as you know, and an STM is just a regular TM in that sense. So you want to cut this aberration, and then you need an aperture at some place. Okay. So usually before the sample, you also have scanning coils, of course, because you want to scan the beam. Otherwise, it's not very useful. Okay. So then comes the second most critical part with the gun, which is the objective lens. So the objective lens, as in a TM, is doing all the job. Okay. You can put as many condensers as you want. It will be of absolutely no use if you don't have an objective aperture. So the main question that you may ask, and it's the same for TM, is that what is the real difference between an objective lens and a condenser lens? And in the case of STM, it's very, I think, a relevant question to ask, because after all, as you see in this diagram, which is not to scale, with this condenser lens, you are able to make a probe, a sharp probe, or even sharper maybe here. So what's the difference? The difference is that this guy is not to scale at all. And in the objective lens is very strong. It has a very short focal length, which means it makes very huge angles. So the real responsible for making the probe is the objective lens. Okay? And because there is a lot of angles in the objective lens, it has to be designed so that there is the less geometrical and in general sense, there is no aberration. Okay, so you don't want to spend too much time on designing this guy very nicely, because they have absolutely, very small angles usually, but the objective lens is the place where you have most of the angles. And that's also the reason why manufacturer or people making maintenance always told you never to touch this part if ever you open your microscope. So I have a secret. You can touch it, in fact. It's much more robust than they say. But still, small change in the design or small scratch in the inner part of the objective lens can really kill all your resolution, special resolution. Okay. So this is for this objective lens. And after the objective lens, in the early day of STM, and there is still STM like that, you don't really need to have optics. So because now you want to make so many things that you want to work a little bit to design the shape of your beams after the sample, because you have many use of it, but you don't really need it. It's just the projector lens, and usually this projector lens can be quite with a lot of aberration and so on. So they are not so important. Maybe they can compress a little bit the beam. You have some deflector to align the beam with respect to the detectors I will discuss in a minute. A last point is that in modern microscope, as STM microscope, you have not only scanning coils, but also what we call descan coils, so that these coils here and coils here that I didn't show are working in opposition, so that your beam, even if you scan on large area, your beam after the sample stay aligned with the optical axis. Okay, it's not very worth to consider if you scan small areas, but if you scan large areas, it might having the scan coils may help you remove some artifacts. Okay, and at the end of the day, of the travel of the electron, you have the detector. So this is here only the bright field detector, which is on the transmitted beam, basically, as I said previously. And you may have other detectors, which are usually, as I say, in the form of a ring, annular dark field detector, so at higher angle. And basically, how they work, it's kind of a little bit simple. You have a scintillator, so it's just a material that likes to emit photons when it's hit by an electron. And these photons are sent, on a photomultiplication tube, which is a system which has a very, very high gain. So it's a very sensitive system, and it's also a system that is very fast. So every time an electron is hitting the scintillator, photons are emitted that can be detected by the photomultiplier. So of course, I will discuss a lot about Ronchigrams that are still not unknown for you, but Ronchigrams is essentially a signal that is detected at infinity, or in the, whatever you name it, in the diffraction plane of your microscope. And for this signal to be measured, you usually need a CCD camera. And also, if you want to make a diffraction pattern, you need a CCD camera right here in this place. Okay, so now we have a basic idea of what the column is looking, how it is looking. But now we want an image. So, as there is of course, a very big difference between an STM and a TM, because the detection is a serial detection. You record every pixel one after the other. So it can be a slow process, and it is usually a slow process. So it has some drawbacks, like if you have some drift, thermal drift, for example, in your sample, then you will have a lot of distortion. If you have noise in your environment, you will also have a lot of distortion, and so on and so forth. But there is, of course, a very interesting feature, which is, as you see, so you will have a computer and electronics, which will drive your probe onto your sample, and at each position of your probe, you will detect some signal, say HIDF and BF signal, but of course you can detect any other signal like electron energy loss spectra, or EDX spectra, or cathodoluminescent spectra, or whatever. So this is the strength of the technique. It's not very good if you want to be very fast, and it's less and less true with the advent of aberration-corrected machines, that I will describe tomorrow. But but in the fact, it's not the best technique in non-aberrated machine to make high-resolution image. But it's a very good machine to make image where you need sensitivity. Okay, so just one point when you are doing STM. So this kind of overheads, I saw it already maybe 30 years ago. And 30 years ago, it was like, I don't know, Chinese for people. Because at the time, people were really not, didn't know what a pixel was. Okay, it was a time of, maybe of recording plates or things like that. So now I'm sure you know what a pixel is, and I will not comment a lot about that. But as the difference with a TM, where you can change the resolution just by changing the magnification of the projector lens, here it's the opposite way around. You change the sampling of your beam. Okay, so that's as simple as that. So when you are doing such an experiment like an STM, you always try to figure out what is the best sampling for a given application. Okay, because everything equal, the better the sampling, the better the resolution, of course. But the higher the time the time needed to record your image. So there is always a trade-off that you have to really carefully take in mind. So if you use STM, I think it will become very natural for you. If you never did it, the first time you will do it, just try to think what you really want to do, especially if you have very sensitive materials or things like that. Okay, so I think it's my last slide on the column, and it's a general comment why I wanted to put the electron travel upside down, so not from the top like in a TM to the ground, but from the ground to the top. It's just that there is a very general, I think we can call it a theorem, because it can be proved in some sense. Don't ask me why, how, but it can be done, where you can directly relate it what you see in TM and in STM. Okay, so as you see, it's upside down. So this is the column from TM. So you have a source, you send some a parallel beam, okay, and when it hits the specimen, there is some diffraction of the beam that is recombined in some sense to form an image. And in STM, it's exactly the other way around. So at the opposite of a TM, where you have a detector which has a lot of pixels, which has a sampling, so the detector is sampled. Here it's the source itself, it's the probe itself that you will sample onto the specimen. So the source and the pixel of an image are directly similar. So if you follow the path, you see how it looks the same, depending on the position of the source. You enter the objective lens, and you will focus on different parts of the specimen. Just like on different parts of the specimen, there was a ray path on different directions. And then the probe is hitting the specimen. And now the detector is an integrated detector. There is no resolution in the detector. It's a BF. Like the source was just a point or a smaller area. So there is a direct analogy between both of them. I show this because everybody is doing that when making a lecture on STM. I will not say that I really like it because the question is, okay, that's very nice. It's a little bit conceptual. So what can you do with that? And in fact, it can be helpful if you are a skilled TM guy. Because if you are a skilled TM guy, you know every prime that you can have on your column. And it turns out, if you discuss with people from the TM coming to the STM, that when we see a prime and we fix it, they have exactly the same prime and they fix it. So I give just an example. It may happen a lot of time in an STM that you see in bright field image some astigmatism. Okay, you have some astigmatism, and it's very odd because you spend all your day or all your morning to align your column, and usually you align your column not on the bright field but on the HADF signal. Okay, so maybe I will say a word on this tomorrow, but just remember that usually it's HADF that is the best signal to make your alignment. And then suddenly you put your bright field detector and you have a huge astigmatism. It's something very, very strange. And this can happen just because the detector is off axis. And if you know a little bit of TM, you know that, so having a detector off axis means that you will have an angle here, okay, between the detector and sample. And if we translate it with the reciprocity theorem, it means that you will have a source which will send a beam with an angle. And most probably, or maybe not, I don't know, but in a TM, when you have an angle, it induced some kind of fake astigmatism. It's not a true astigmatism. It's called, I think, tilt-induced astigmatism. But in any way, if you make a TM and just try it once, and you put an angle in your incoming beam, you will see some astigmatism. And it's exactly what happened in STEM in the other part of the STEM. So it can be, in few cases, very interesting to make the comparison. But for that, you need to know very well TM before. So sometimes it's a little bit not useful. Okay, so far I just talked in a very general manner about the probe, the electron probe. So now we want to know how we can make a probe and how we can characterize it. Just before that, before discussing the probe, I have to discuss the signal in the diffraction plane. So now I think it's almost clear that at the end of your STM, you have a place where you really like to put your detectors. On this plane is what you would call in a TM the diffraction plane. Okay, so it's the plane which is at infinite distance from your objective lens, or it's a Fourier plane if you have a lens. Okay, so the signal we want to use for imaging in a STM will be for essentially bright field, the transmission beam here, which is something like 90% of the signal, which is here. Then you have all the signals that come from diffraction, so bright spots, so maybe it's 9%. You have within this plane a lot of inelastic signal, but it's spread almost all over this, what I call electron, but it's what the signal you would measure in yields, for example, and it's say 1% of the total signal. And then at very large angle, you have what is sometimes coined as pseudoelastic, so it's all the scattering from phonons, and it's less than 1 per 1,000, typically. And as we will see, bright field will be mostly here, and high angle annular dark field here, and in most of the TM, in fact, people are using a little bit, or sometimes a little bit too much, maybe, a little bit of also the bright spots for the dark field imaging. This is a very important quantity. Of course, if someone is there and aligns the STM for you, you may never use it or having any reason to know about it. But if you really want to make STM experiment by yourself, it's worth knowing it. Just by the way, I was using STM for 10 years before I learned about Ronchigrams, so you can still use STM without knowing it. Okay, so before Ronchigrams, you need to know how electron probe is made in an STM, because a Ronchigram is just another way of looking at this probe. And of course, the size of the probe, the probability of the probe, is what will determine the resolution and the sensitivity of your apparatus. So you really need to take care of it, just like a small baby, because a lot of time it's very easy to make it wrong. Okay, so this is still this basic STM I was discussing at the beginning. Now it's on the side. I'm sorry for that. It's on the side because I just wanted to make it just like an optics with photons, an optics system. So it's very simple. Your gun is somewhere very, very far away, and you have one condenser which collimated the beam, so make it parallel. And we send this beam on the objective lens. So usually in a stem, the beam is entering the top part of the objective lens parallel. And of course, if we put the sample here at the focal length, due to geometric optics, we will form a probe, an electron probe, right here. So this is here just growing with geometric optics, but of course, as you know, electrons are quantum beasts, and when you are using STM or TM, you really have to consider it. So in fact, if you look at the density of electrons that has been formed in that way, you will see that you have, in fact, an array function, which is, in a word, just a very peaked function here, and you have some wings here, some oscillations. Even if you have no aberration, right? So it's really a perfect case, no aberration, infinitely parallel beam that comes that hits the objective lens, and that is cut it by an objective aperture. Okay, so there is this shape. So there is a mathematical formulation for this that I give it to you, and the only point that we really want to remind is that if you were in a perfect world where the objective lens would have no aberration, where you could have an infinite intensity with an infinitely small source, then the limit in the size of your probe, okay, the distance between the maximum and the first zero, will be inversely proportional to the angle here, maximum angle of incidence, and proportional to the wavelength of your beam. So just like in a regular TM, it's not a big difference. If you want to have better resolution, if we think, which is not totally true, but if we think that resolution is ultimately given by the diffracted limited probe size, then you really want to decrease the wavelength of your electron beam. You want to increase the energy, just like in a TM. And of course, you want big angles, very big angles. And that's the reason why it's sometimes much more easy to understand aberration correction in an STM like an TM, because it's really directly obvious that if a way to make a small probe is to increase angle, then you have to correct for any aberrations that will come with a high angle. Okay? So if you want a small probe, you need either or both of them, either a low wavelength or a high angle. Okay? So this is for a perfect world. But if you really want to ask what is the size of the probe, then it's worth talking more about incidence angle, because the true quantity, which is perfectly defined, is the angle of incidence if you are diffraction limited. But in fact, as I said, you have a lot of aberrations with broaden your probe, and also your probe will have some amount of uncoherency, just like in a TM, that will broaden it even further. Okay, so I will talk a little bit about aberration, and tomorrow I will talk how to correct them. So this is a perfect wavefront coming onto a lens. So this is a sphere, in fact. And if you have a perfect sphere, a way of discussing a perfect sphere is to say that an incoming spherical wavefront will be converted into another spherical wavefront. So this one is diverging and this one is converging, but it's just what a regular lens is doing. So the ray paths are perpendicular to this surface. So you see that this point is becoming this point, and because everything is perfect, if you increase the angle, this point is still converted at this point. Of course, this is not the case, and lenses have imperfection, and this imperfection can be scheme as a distortion of the wavefront here. Okay, so it's not a sphere anymore, it's something, I don't know. And the ray paths, which are still perpendicular to this wavefront, you know, it's at small angle it's almost the same, but at large angle, the ray paths are pushed towards the center of the lens. So you have aberration because this point has been imaged here, and in fact it's a continuous distribution of images. So this is aberration, and that's why usually you want a small objective aperture. So where do the aberration come from? So there is a chromatic aberration. I won't discuss it. It's already enough work to work with geometric aberration. And because today it's not the point of talking about aberration correction, I just give here a transfer function for a stem here. And if you remember the TM lectures, it's almost identical to TM aberrations. And there is no reason why it would not be. I discussed with you about the reciprocity theorem. So for bright field, it has to be exactly the same. It's not exactly the same for HADS, to be honest, but for bright field, it's exactly the same. So it's totally identical. And all the concepts that you have in non-corrected TM, like scatter focus, exist for STEM. Okay, so I won't comment on that. And I just want to point this out, just to say also that it's not because you are doing STM that you are not doing something serious. So what I mean by that is that whatever comes out of a microscope may have to be compared to simulation at some point. And it's absolutely not the topic of my talk to discuss about that, but you can do a lot of image simulation for STM like you have to do with TM. It was not as easy to do maybe 10 years ago because it's a pixel per pixel imaging process where you in fact have to have an image of all the diffraction pattern at each position. It's very time consuming, for a computer, but now it can be done. There is free software for that. So don't think it, because it looks like an STM, you will have no effort to do. You will have to do some at some point. Okay, so this is all the aberration up to 5th order that you can have. So it's just to make you a little bit afraid for tomorrow, because we will discuss essentially this kind of things tomorrow. But today, I'm sure I want to stay friend with you, so I won't comment a lot about that. I just want to point out that aberration, geometric aberration, essentially, are a deformation of the waveform in many different manners, and that's it. That's the only thing I wanted to coin now. Okay, so now the Ronchigram. So why is the Ronchigram, and what is it? So the Ronchigram is a very generic term, and this is just a contrast that forms in the diffraction plane. So most probably, if you have been using TM, you for some application, you have been focused your beam on your sample and maybe make an image of this beam, or a diffraction pattern of this focused beam. And what you have seen was the Ronchigram, but of course, maybe in a slightly different manner. In fact, of course, in this diffraction plane, depending on how you make your illumination, is it parallel, is it convergent, and your detection, are you detecting just one very little part of it at small angle, at large angle? Are you integrating all the information? Are you having a little bit of sampling on your detector? The Ronchigram can be coined as sected area electron diffraction, the one you already know, pattern, sorry, seabed pattern, convergent beam electron diffraction pattern. It can be a projected image, as we'll see, and many other things. So it's like a chameleon, I don't know. It's kind of lizard that change color depending on the need. And exactly the same. And the reason why people are always talking about Ronchigram is that really the way to understand and to measure aberration in an STM. Okay. So just to explain, or making another view, I will just comment about convergent electron beam diffraction mechanism. So you send a parallel beam on your objective lens, which will focus the beam onto your sample. And if you just consider the transmitted beam, it will be a disk and not a spot, like if you would have a parallel illumination, it will be a disk. And of course, because there is some diffraction, you will have another Bragg spot that will be broadened because you have some angle of incidence, and another one, and so on and so forth. And the Ronchigram I will discuss is essentially concentrate on this part, okay? The central disk, where sometimes in crystalline system, we'll see one or two examples, there is an overlap of different Bragg disks, okay? So I just show it to you because maybe some of you did some convergent electron beam diffraction. So there is nothing very mysterious about the Ronchigram. It's just a broad disk, and this is the information that are inside, which will be of interest. Okay, so here I will try to explain why it's a good way of characterizing your electron probe. So what you see here is an image. I will explain which kind of image in a minute. It's an image of a carbon foil with some nanoparticles of gold, maybe 20 nanometer in diameter, 10, 20, 30, whatever. And this image has been done in the diffraction pattern by imaging the central spot. Okay? So if you ever done, seabed or things like that, it's what people call the shadow image. So you have really an image of your sample. So assume your sample is here, so this kind of sample, for example, and the focal plane is here. So you have under-focused your beam. You have put your beam after your sample, and you try to it's a perfect case, perfect image, perfect lens, perfect STM, and try to understand what is the image of some object which is close to the axis. Okay, so you make, it's even not geometric. I'm sure a kid could do that. It just, you will have just an image of this guy inversed, okay, and magnified. And the magnification of this image will, of course, depend on the position, relative position of the object plane and focal plane. Nothing mysterious. So now, you may ask, okay, but what happens to an object that is off axis, like this red one? But you see, you make exactly the same drawings, the same size of the object, and the image is the same size. Okay? So this is exactly what you see here. In this plane, you have a lot of small dots at different positions, which correspond to different angle position. And the image of each of one is almost the same size. They have not all the same size in reality, but there is no big difference. So basically, Ronchigram is just a projected image, so nothing very interesting there. But if you want to very quickly survey an image, okay, this is exactly the same but over focus, so not a lot of importance. If you are exactly on focus and you look what is inside your Ronchigram, there is absolutely nothing. It's a flat. It has to be a totally flat contrast. So there is small defect because we are in real life, but it's almost flat. And the reason is, of course, you have here an infinite magnification. So just a magnification of something which is infinitely small and that contains absolutely no information or a constant information. So you are you want to have absolutely nothing inside this disk. Okay. So this is for the perfect case. So now assume you have some aberration. So again, we'll see tomorrow exactly how it works. But the point is that, as we saw, at small angle you have one plane, one focal plane, and at high angle you have another one. Okay, so you have two kind of, say for these two rays, you have two different focal points. Okay, so the consequence, which is came here, is that close to axis you have a given magnification for a given size of the object, and if you keep the same size, keep looking at an object of the same size, but now a little bit off axis, then you will have, in that case, an increase of magnification, right? Okay, so this is exactly what you see here. This is comma aberration for what it matters. And if you look at the shape of an object, which should be a disk or a sphere, here it's almost spherical here. But when you go at high angle, the magnification, the local magnification is changing. So it's just stretching the object at high angle, as you see here, and compress it on the other side. Okay, so it's really typical from comma aberration. And the point is that you can see it in 1 second. You don't need to have to know any equation about that, any physical ground. It just you can understand it just by geometrical optics, and it's great. And this you can see by eye. And of course, here it's on a dedicated machine, but on the GOL that you have here you can make this kind of measurement. Not for comma, which is too high another aberration, but you will see how aberration, spherical aberration can be detected. Okay, so this is here. So now you are getting closer to the focus. Okay, and so close that there is at least one object, says this one. So you are getting closer to the focus. Sorry, so the focal plane is here. And now I'm trying to look what happens to the image of these three different objects that have all the same size. But now we are a little bit closer to focus, so it will, in a sense, magnify the effect a little bit. So this guy, which is very close to the axis, have an image with some magnification. The second one is has a size that is increased, and this guy may have something like an infinite magnification. Okay, and this is typically what you see here. You have a place at small angle where the object keep a constant size, and at high angle, so high distance on the Ronchigram, you begin to see this like line here. And this is what is called something like a circle of infinite magnification, and it's typical from aberration correction. So the place where aberration do not arise, it's sometimes coined as sweet spot. And this is, of course, with this part, this angular part of the beam that you will make your probe. Okay, and that's the most important slide of on the Ronchigram. You can maybe even forget everything else of what I said. The Ronchigram is really the place where you may want to correct your aberration. But if you have a non-aberration corrected machine, what can you do? You can correct the stigmatism. So you can do it on the Ronchigram. Yes, okay, I didn't put it in my, on the slide. But you can correct it directly on your Ronchigram, and assume you did it. You will see a lot of third-order aberration, spherical aberration, third-order spherical aberration around that. And this you cannot remove with any tricks if you don't have corrector. So what you want to do is put an aperture that will filter out all this information and just keep that one. Okay? And if you don't have the Ronchigram, you will most probably never know where to put this aperture. If you have a Ronchigram, you just look where you have this sweet spot, and you align your, if you are a TM, you align your condenser aperture so that it is centered on this guy. And then it's done. You have the best probe for the condition, the specification of your TM. So it's very important that you look at the Ronchigram and try to locate where there is this sweet spot. So this is with that you will have the best probe. Okay. So there is other use of the Ronchigram, and I just cite one, which is for orientating a crystal. So don't be surprised. It's exactly like you will do maybe in a seabed or things like that. You see here, this is a Ronchigram. So it's just a diffraction pattern, convergent beam diffraction pattern on a crystalline system. And here you see you have an axis, a zone axis. So you can tilt and monitor the change in the tilt by how this guy tries to go align with the central beam. And when everything is aligned, you have something like that. So this is an uncorrected machine after David Muller. So it's very, very useful to have this kind of to have a way to look at the Ronchigram. And it's kind of easy if you have a regular TM, not a regular STM, but a regular TM. You just have to look in diffraction mode at your diffraction pattern. Okay. So now that you know more or less how you align your system, your STM, you want to make image, and it might be time to make image. Yes? Okay. So again, the take-home message is that HADF is essentially an image of the material. It's just white when there is material and black when there is no material. And a bright field is exactly the other way around. So for the moment, forget about these two images. This is some material here. And this is a bright field image with a detector, which is exactly the complementary of the HADF detector. And you see how both images are complementary. And hopefully, because you send images and on a thin sample, so you think that every electron have been scattered, but in the direction of the electron beam path. So it has to be detected somewhere. And in this bright field with a very high angle, you have some of the electron, and the rest of the electron have hit the HADF detector. So it's with the sum of both. If you sum both of them, you have a constant contrast. Okay, so they have to be complementary. In the fact, usually bright field images are taken with a detector which is much smaller, and I will discuss this at the end of my talk. So I will now concentrate on dark field. So dark field is all kind of signal, in fact, that you can form by excluding the central disk of your diffraction pattern. Now the theory to first order, and it's already kind of a little bit complicated, at least for me, because it never really works, but it has to be presented this way, is that in the early days of dark field theory, the idea was the following. You have an atom, you send an electron beam, and the potential of the nucleus, okay, not the core, the nucleus, sorry. The potential of the nucleus is deflecting the electron beam. That's a very well-known mechanism called Rutherford scattering, and there is a very well-known formula where Z is atomic number of your object. K0 is constant related to the wavelength of your beam, and theta is the angle of deflection, and theta 0 is a typical angle of deflection. It's typical angle of deflection. So it's essentially what this cross-section means is that the probability of being scattered at an angle theta varies as the square of the atomic number divided by something which is, I will not call it real Lorentzian, I don't think so, but some kind of function that is picked at 0 and which has a finite width. Okay? But what will be very interesting for us is that it's dependent on this atomic weight. So now if you want to include inelastic scattering, because this was inelastic scattering, you have another formula, and they are kind of close, in fact, more or less, for this part. But you have this extra dependence in angle, and the prefactor in the atomic weight is a little bit different. This is Z squared and Z here. And of course, it's not just a detail, and there is, I think, like a constant fight in the community to know if the HADF signal is proportional to Z squared, or Z at the power of whatever you want. So I'm not an expert at all. I will never ever enter the discussion. You just want to know that it's related to the atomic weight, and then you have to make simulation if you want to go the step further. So then this dependence has a very interesting consequence, which is it's a mass and atomic weight dependence. So HADF is essentially a map of the mass under the beam, okay? The total mass under the beam. It will vary with the atomic number of the object and the thickness of the object. Okay? So just to show you the two different inelastic and elastic signal, and how choosing the angle of detection may change things. But low angle is inelastic scattering, which is much stronger, while at high angle, this is the elastic scattering. And you see here, we are already at 100 millirad. So it's kind of a high angle. And as a rule of thumb, if you want to have a real high angle annular dark field, you may want to work at 80 millirad, which is in many microscopes kind of difficult. So if you want to be free, essentially, of most, if not all, diffraction effect, you may want to work at very high angle, but in most of the case, it's not possible. So I will discuss this in a minute. Okay. So you may want to make atomically resolved HADF, and you can do it basically with you need a good machine, but 2010 with a Schottky gun, do it quite properly. If you have a large lattice parameter, say 3 angstrom, it should not be a problem, typically. If you want to have 1 angstrom, it's a problem. It seems that it would be very nice, because I told you, okay, HADF, it's just something proportional to a certain power of Z, of the atomic weight. So if I have a nice crystal which is well aligned, I should have very nice images of the atomic column, just like maybe the one I showed you at the beginning. So this is right. You can make very nice things, but don't think you avoid any of the problem you have in high resolution TM. Okay, because the electron that you send on your sample are still waves in the quantum sense. And when you have an electron probe which is smaller than the typical distance between two electrons, for sure you may have a lot of effect like channeling, just like in a high resolution TM, so that for example, your electron will stick on a given column. So you will have a kind of auto-focusing, which will not be, which cannot be described by any means by any geometrical approach, and so on and so forth. So of course, naively, it will be a projected image. But if your sample is on axis, it's just much too naive, and then you have to make simulation just maybe in the frame of block waves or multi-slice, just like you would have done in a high resolution TM. So again, the message is HADF STM is very nice to have a large sensitivity, a lot of contrast. But if you want to make something quantitative, then you are stuck with the same problem as in high resolution TM. Sorry. So this I will not comment. It's just for you to have it. If you really like this field and you really want to understand how HADF contrast forms, there is really a bunch of literature of specialists that really treat and still try to go very deep in the understanding of HADF contrast. So I don't know, it's vacation time in Brazil. Maybe you have a lot of time and you can read all of this. There is maybe more exciting things to do with the life. Anyway, so I want to point to the real interest of using HADF. After all, it has a cost because you have to transform your TM in an STM. And if you want to make an image, why not using a TN? So again, the most interesting thing is that, as I say, you are imaging the thickness and atomic weights, or a combination of both. So here I'm citing this this work, which is a very, I would say, academic work, which where the goal was to prove what I'm trying to tell you. So it was some weights of silicon and silicon germanium, okay? And the nominal germanium composition was changed from one wedge to the other. And what was measured is the HADF intensity in some arbitrary units as a function of the thickness of different alloys of silicon germanium, okay? So you start here with pure silicon, and then you increase the content of germanium, okay? And germanium is heavier than silicon. So when you go from a small, say at a given thickness for a small percentage of germanium, you have less intensity than for large. And in fact, it can be proved to be kind of proportional to the stoichiometry, the change in HADF signal. And now if you increase the thickness for a given composition, so for a given percentage of atomic numbers, then you see that you have spread lines. So it's proportional, but it's proportional for not too heavy atoms and not too thick samples, because here you see you begin to have curvature. So this kind of consideration has to be taken with a lot of caution, because what I said, okay, that is proportional to thickness and atomic weight, become wrong very quickly. For example, if you have constrained objects, and especially if you don't take very high angles, if you have thick objects, as you see here, and when you are doing high resolution, or to be really, really clear, when you are working along zone axis, where you can have the channeling that change the ratio, the intensity, sorry, of HADF, of the HADF signal. So be careful with that. So this is another example taken from the same authors, same paper, where here you have something of known thickness, and now you have different parts where there is germanium with different composition. And now the thickness is known, so you can determine almost exactly the percentage of germanium in each, what is the HIDF? That's a good point. It's here. So this is places where there is germanium, if I'm not saying something stupid. So this has been normalized by the thickness, and you can be even quantitative in the determination of the composition. But you have to be very careful when doing that. Okay, so sorry for Luis, because I trained it as quick and dirty, but it's a very important use of STM. Here you have a nanowire made up of GAN, here and here in white, and ALN in black. I think today, Louis Agonel will tell you what is the interest of this kind of structure. But here what I want to point out is that it's a sample which is a lot of structure and a lot of difference, because aluminium and gallium have not the same weight. So that's the reason why this part is brighter and these parts are darker. But it's very easy, it's very quick at least to make this kind of image. And very quickly you have direct chemical information. So it's not quantitative, but qualitatively it's very quick to have, and it will be much more difficult to do by, okay. So this is another example. It's a non-aberrated machine, and this is palladium, I will say cluster on this side, just to show that you can detect very small amount of atoms. This is on a carbon foil. And this could not have been done in an uncorrected TM machine. So if you have something very heavy, and it may happen that if you have chemists, you have things that are heavier than carbon. If you are unlucky on making, of course, organic chemistry, it's not the case. But if you are making an organic chemistry, and we have a lot of people coming to us for this kind of application, it's really the technique of choice. There is many chemists coming to our lab. They didn't know about HIDF, and then spent one day with us. And then when they came back, they didn't want to touch a regular TM anymore. They wanted to make HIDF. And the reason is the sensitivity of this kind of apparatus. Okay, so this is what I was saying. If you have heavy atoms somewhere, you may want to use HIDF. If you have some chemical contrast that you want to know, maybe not in a qualitative way, but in a quantitative way, but in a qualitative way, it's worth considering HIDF for your application. If you really need sensitivity to small amount of heavy atoms, there is no doubt that you may want to consider HIDF. If you are not so interested in the resolution, just like the first experiment by Crew, where you saw these uranium atoms, of course the size of these atoms as image were much larger than 1 angstrom. But the point is that they were able to detect 1 atom. As I said, it's especially true in many aspects of material science and chemistry. Just a comment on the angle. It's at first I wanted to make a long story about angles, but it's very difficult because it really depends on any machines and so on. So I just want to give you a simple message. Again, it's a work by David Müller, which is someone who made a lot in this field. Here you have an interface between a crystalline silicon and amorphous silicon, and you have a small layer on silicon oxide. Okay, and I can't remember exactly why they did it. Maybe they did it just as a proof, test proof, but it's very nice. What they did is that they took 2 different dark field images with 2 different angle, inner angle for their detector. So the good way to do it in a TM is just to change the camera lens of your apparatus. Okay. So in that case, you have high angle hitting the dark field image. So this means you have a very short camera lens and and here you have larger camera lens. I hope I did it in a good way. Anyway, in this case where you have large angle, it's almost only a current signal, and you don't see much as the interface. But here, where you have small angles and you have a lot of black spots, maybe maybe it's lower zone, I don't know exactly, but maybe it's black spot. Sorry. just as the interface, you see that the contrast is totally different, okay? And the reason, the physical reason behind is that you have a strength field. And this strength field induces the channeling and small angle diffraction. And if your detector is not so large that you remove all diffracted signal, then you will have more signal where there is more strain, and then you will detect this feature, which is not, I would say, a real structural signal. It's not because it's more thick or whatever. No, it's just because you have a strain. So be very careful. And if you look at this kind of sample and you want to make HDF, I really urge you to read papers, especially by the team of Müller. He wrote also by Pennycook. There is a lot of literature on this aspect. So be very careful on the choice of the angles. So you can make something very qualitative, not choosing the angle, but if you want something quantitative, be careful of the angle. Okay, so the last part of my talk is discussing a little bit on bright field, in fact. So as I said, if the inner angle of the HADF dark field fits with the outer angle of the bright field, you have, of course, something which is totally complementary. Okay. But if now you take very small angle, here in that case 3 microrad, which has to compare with maybe here 80 microrad, then you have an image which is very close to high resolution TM image, or maybe it's not really high resolution, but like TM image, bright field image. And of course, or maybe I guess at least, when you had lectures on high resolution TM, it has been maybe coined as coherent imaging, or maybe someone told you, okay, it's a phase. You are measuring the phase of the scattered electron. Tutorials in optics, diffraction tutorials, you move your grating, and you will see that the fringe will move on your diffraction plane. It's exactly the same. So the idea of bright field imaging is that you will take a detector which is smaller than the typical fringe size, typically, and you will move the probe, and you will record the change of this intensity, or this intensity change as a function of the probe position. And then you will have a current imaging, even if you are using a probe. This is what I try to scheme here. So it's a easier situation. You are not in zone axis. You have only two beams that are overlapping. In red here, you have your bright field detector. And because you have a crystal, these two beams are interfering and making a pattern. So say in black, there is no signal, and in white, there is some signal. So now you move your beam by something that is less than the distance between two atoms. And you see that now the detector, instead of being on a dark position, was on a white, is now on a white position. So if you record the change in intensity as a function of the beam position, you will see modulation, fringes. Exactly like in TM. In high resolution TM, what you see is not a direct image, it's just an interference pattern. And this is exactly the same, but it's another way of seeing the thing. So that's why bright field image is a coherent imaging. And just as a rule of thumb, is you want to be really coherent, you have to use a small detector, which will be smaller than the typical interfringes spacing. And if you take a larger one, it can be interesting, but you will begin to make some incoherent imaging, or maybe something which says a little bit incoherent or not coherent. It may be tricky. So in that case, maybe worth making HADF. And as a final word, I would say coherent bright field is identical to high resolution TM. So this is not a proof, but it's just to say that now it's a reality. So this is an image making by a corrected machine, but maybe a TM, maybe a STM, and exactly the same. Well, here it's another kind of carbon nanotube, but it's a corrected machine by another guy making with another brand of machine. And in fact, this is parallel beam high resolution TM, and this is a bright field convergent beam TM, STM. and there is no much difference between both of them. Okay? So now we have reached a point where making one of the other is, in terms of contrast and resolution, almost the same. But of course, if you want to make a resolution image, it may be still worth doing it in TEM because it's quicker, a little bit quicker. Okay, so let's conclude my lecture. So first of all, I said it, I didn't prove it much, but keep it in mind. An STM is a technique not only to have structural information, but also to have spectroscopy information, and both at the same time. So it's very, very important. Otherwise, it may not be that interesting. HADF is roughly a projected image of the mass under the beam. So to first order it works, and for most applications, it's enough to know that. It's then perfect for imaging small amount of heavy atoms or to have chemical contrast, at least qualitatively. You can make coherent imaging with bright field. I don't know if there is a bright future for it, but you can do it. When you begin to work at very high resolution, HADF or bright field in an STM have exactly the same kind of problem of high resolution TM. You cannot avoid making simulation in that case. You cannot avoid knowing every relevant angles in your system, which are incidence and collection angles. You need to know exactly what the acceleration voltage and so on and so forth, exactly like in TM. And finally, you have met this strange beast, Ronchigram. I hope you really like it because tomorrow you will have a lot of Ronchigrams. So there is many information in it, and there is one fundamental. It allows to diagnostic aberrations and to measure it. And in a sense, it's very nice to have this object in STM. You don't really have the exact counterpart in TM for aberration correction. And my feeling is that much more, you understand much more things with the Ronchigrams than with any other quantity in TM or STM. Okay, so I thank you for your attention. And of course, I'm really open for any question now at the coffee, if you let me have a coffee first. But after my first coffee, it would be really my pleasure to discuss with you. And if you have questions in 1 month or 1 year, just drop me a mail. If I can answer, I will answer. If I cannot, I will try to send you to someone who is an expert in your question. Okay, I thank you for your attention.